are. It's the physics video lecture, Physics 2A video lecture 25. So we're starting a new chapter. We left off with some rotational formulas from the beginning of chapter 7 actually. So we're not taking things in complete order, we're taking things in logical order though. So I'm going to go ahead and write up those formulas again. Remember we had a table of linear versus rotational quantities, and then we'll continue to develop the subject from there. So this is a, let's see, I'm going to split the board as it were, and I'm going to put rotation over here and linear quantities over here. And in fact, let's go ahead and just write the linear ones down. We have, okay, this is linear kinematics, so that we have what we're talking about. So our linear kinematics, we have position, displacement, velocity is displacement over time, acceleration is the change of velocity over time. And over in the rotational world, we had angle, we had angular displacement, we had omega equals delta theta over delta t, and we had alpha for the angular acceleration. I'll write some of these things down, delta omega over delta t. So the construction is exactly the same, except instead of along a straight line, we are rotating. Okay? And again, this black slice here represented 1 radian. 2 pi radians gives us 360 degrees. Yeah. So those were those definitions. And I'm just going to continue. So what we had here was the angle, and theta is measured in radians. We had the angular displacement, I'll abbreviate that, angular displacement, and that is also in radians. We had the angular velocity. Angular velocity. I have to get used to writing omega. It's not a W, it's an omega. Okay. And this was in radians per second. And then we had angular acceleration. I'll abbreviate that. Angular acceleration, and this is in radians per second squared. So that the way these concepts are constructed is the same as they were constructed here in linear kinematics. And when we get to constant acceleration, then we have the constant acceleration kinematics, and we're going to have the constant acceleration rotational kinematics. Okay, so that's going to come on the next board. This is a nice table to have in front of you because we've learned this and we can inherit what we learned. So then coming underneath here, constant acceleration, that means constant angular acceleration. So alpha is constant. And here we have, if acceleration is constant, and I'm aiming down to the second part of the table here, then we have our formulas. That we use for all manner of problems, right? And V0 plus AT, V squared, V0 squared plus 2A x minus x0. So these we studied and developed really systematically. Here, we're just going to inherit the form that we have over here and translate it into rotational quantities. Yes, we can do that. So we have for our rotational kinematics, we have theta equals theta 0, omega 0 t plus a half alpha t squared. So that's constant angular acceleration. Constant angular acceleration. And then we have the omega 0 plus alpha times t. And the one where you eliminate the time plus 2 alpha theta minus theta 0. Good, so we have those. And what I had said at the end of the last hour was that we could extend this whole conceptual list into dynamics, okay, which is what we're going to do. Now, before we do that, I have to write down the relation between linear and rotational quantities. So actually I had a couple of definitions here. I put them up last time as well. We had 1 revolution equals 2 pi radians, because we're often asked about revolutions. So it's just a conversion factor, and RPMs I did as well. Okay, but there's also a relation between linear and rotational quantities that we have to talk about. And that is if this disk here, thinking it's in the picture, if this disk is rotating, then every point on the disk is of course moving as well, like this red dot here is moving. And the question is, how fast is the red dot moving, or any particular point, how fast is it moving if we're rotating with a certain angular velocity or angular speed? So what we're asking about is the relation of linear and rotational quantities. And this is actually comes right out of their definitions. So we have, let's imagine we've got a wheel here rotating about this axis, and I'm going to draw this kind of like that slice I have right there, but I have an S and a theta. And if we imagine this thing's rotating counterclockwise, I kind of do that counterclockwise arrow there and refer to that as omega. So this disk is now rotating counterclockwise, just like this one here, with rotational speed omega. Okay. So from our original definition, and there's R, okay, from S equals R theta, we have delta S equals R delta theta, and therefore I'm going to draw my conclusion over here. Delta S over delta T, that's the speed of a point on the edge here as it rotates. Okay, so delta S over delta T is V, but on the other hand, it's R times delta theta over delta T, and that would be our definition. Delta theta over delta T is omega. So that is equal to R times omega. So what I'm saying is that V, which I'm going to underline in red, is equal to R omega, and I'll use this part of the board to draw this. So very important addition to this whole list here, we have for this relation of linear and rotational motion, we have V is equal to R omega, and we could put a little T here for tangential if we want to talk about it. It's the tangential speed, but right now we're just going to call it the speed. Okay, it's the speed. It's not a velocity, okay, but it's a distance over time. Okay, So V is R omega, and by the same construction, acceleration equals R alpha. Now here I am going to put the T here for tangential because we've already talked about a centripetal acceleration, and this is not the centripetal acceleration. Tangential acceleration is the acceleration of a point. If this thing's rotating, that's the acceleration of that point in the direction tangent, okay? Not radial, not towards the center, but tangential. Good, so the T refers to tangential. And these two formulas are added to this list, say on the left side actually. Okay, so very important formulas that relate rotation and translation, or rotational motion and linear motion. Relation of linear and rotational quantities, right here once again. So yeah, this is very important. Add it to that list. And good, then we're on our way. So we did a couple homework problems, and you can make up as many problems or look up some problems here because these are done just like these, okay? I'll go ahead and go back and work those next week. But for the moment, we want to continue on with these rotational quantities. And the next concept we need is the axis of rotation. So this disk is rotating on a little axle, and we can think of axle and axis pretty synonymously. The axis of rotation is pointing towards the camera, right? There's the axis of rotation. So we need to spend a little time talking about the axis of rotation. So next is the axis of rotation. So when you have a wheel that's rotating, good, there's the axle, it's the axis of rotation. So one example, axle of a rotating wheel but then there are many things that rotate. For example, if you swing your arm like that, it's rotating, and the axis of rotation would be right here in my shoulder, okay? Again, pointing at the camera. So that's an axis of rotation. In fact, if I turn like this, then you could say the axis of rotation is vertical through my body, okay? So everything that's rotating has an axis of rotation. And I'll just give an example. Suppose we had a board here and we had a nail through it, and we could let the board swing back and forth. Okay. Then this would be the axis of rotation. Okay, if we were going like this, back and forth. So this would be the axis. And again, you could look up and invent many different axes of rotation. So when we have an extended body, is what we call this disk, it's the extended body, it's rotating about an axis. If I have this bar here and I turn it like a propeller, there's the axis of rotation as well, right? My arm then you could say is the axis of rotation, rotating it like a propeller. Okay, so now we're talking about rotational dynamics. So next here is rotation of an extended body, or just rotation of a body about, and not its axis, an axis. There are many possible axes. So many possible demonstrations check. You rotate wheels, you rotate this thing, I just showed you those. What we want to find now is what is the kinetic energy of a rotating body. Question: what is the kinetic energy of a rotating body? This is pretty interesting because it's not going anywhere, and yet every mass that comprises this body here is moving. Okay, and if it's moving, every individual mass should have a 1/2 mv squared. So good, I'll just draw a rotating body. Imagine you have some disk here rotating about this axis like so, and it's a massive disk. So what is the kinetic energy of that thing? We'll start with, it's the sum of all of the kinetic energies. So that's a summation. I equals 1 to very, very many. It's a summation of all the individual kinetic energies of the masses that comprise the body. Now watch this. We can pull the 1/2 out, of course, right? We've got a sum of the individual masses and their speed squared, but their speed is r omega. So I'm going to write r sub I omega squared, because every mass in this rotating disk has the same angular velocity. Okay? The disk has just one angular velocity for it, and that's omega. So when I do that, I can say kinetic energy, and I will say sub-rotation like that, is 1/2, I'll put in parentheses, sum of m sub I r sub I squared, omega squared outside. Okay, this has to be discussed a little bit, so I'll rewrite it and discuss it with you guys. In fact, I'm going to rename that R there. So once again, the kinetic energy of rotation, I'm going to rewrite it for you. For kinetic energy of rotation, it's 1/2 sum over m sub I, I'm going to write L sub I squared, it's just another letter, but it's important because this is the distance from the axis of rotation. It's not just any old radius, it's distance from the axis of rotation. Okay. So yeah, this is interesting because we have 1/2. Now we have a new quantity that's going to get the letter capital I and omega squared. This looks just like the translational kinetic energy, except instead of the mass, we have something called the moment of inertia. So this object here is called the moment of inertia. So I is called the moment of inertia. You could just as well call it the rotational inertia. Moment of inertia. It is the resistance to twisting. And we're going to have to talk about torque and everything to really get the feel for that. But right now it's a resistance to being turned. Okay. And yeah, so this is a really important concept. We actually have a lot of demos for it. Let's see how we're doing here time-wise. Okay, great. So the moment of inertia, it's the resistance to being twisted. When we talk about torque, which is coming up, we'll see more of that. But this is an interesting example I already shown you. But looking at these bars a little more closely, we see that they're the same length and they have the same amount of metal. Okay, so there are these nicely machined aluminum or steel dowels here. So this one bar has them at the ends and the other bar has them in the middle, and I'm showing you they're the same length, which is to say these bars have the same mass. It's just distributed differently. And this is something actually everyone has to try. And you're not here, but first I'll demonstrate. You can try this with other objects as well. This one twists like that. This one here, if I try to do the same thing, it's much more difficult. Okay? It has more resistance to turning because the mass is at the end. And this expression here is about mass distribution. Okay? So if most of your masses are at the end, then these L squareds are much, much larger. Okay? So even though this thing seems the same, weighs the same, if you try to twist it, this one's twice as difficult to twist as this one. At least, it's much more difficult to twist. Okay? So the moment of inertia is it's not just a mass, it's a mass distribution. And it has the dimensions kilograms times meters squared. So let's add that to our thing. So the units, I square bracket kilograms meters squared, and this is a mass distribution. So as soon as we're talking about rotational motion of extended objects, the distribution of the mass is very crucial. So here's a couple of things you can try. Suppose you have a meter stick at home. You can just grab the meter stick and it has the same, or any stick that you have, any piece of wood, any dowel. You do this, okay, and you'll feel a certain resistance to twisting. Grab it at the end, okay? It's now the same mass, but the distribution is much larger in one direction, okay? And you try to twist it this way, it's much more difficult. So go ahead and give that a try. With a board or whatever you have, a yardstick, a meter stick, whatever you have, go ahead and give that a try. You'll definitely feel the difference between these two mass distributions. And it's interesting, the axis of rotation is of course along the length of my arm right now, towards the camera. We can take the same mass and twist it around this way. Okay, then the axis of rotation is straight through the center of the ruler, and there's no resistance to twisting at all, or very, very little. Okay, but the distances from the axis of rotation are minuscule. Okay, so these L squareds are tiny, and that's why the moment of inertia, if I take this vertical axis, the moment of inertia is tiny as well. Okay, so bottom line, mass distributions play a huge role in rotational dynamics. And so we're going to study extended bodies and mass distributions and forces on them and so forth. And we'll have to study them in some depth before we return to the rotational quantities. Okay? So we've arrived at the importance of mass distributions for an extended mass. It's no longer just a point, it's no longer just a tennis ball. And we now have to go ahead and study that. So that's a new section. And we're now in chapter 8. In fact, this discussion right here comes fairly late in chapter 8, but you see I'm building it up logically. So we've come to the discussion of mass distribution. So this is extended bodies, mass distribution, we'll talk about torque. Okay. So this is good, this is good. We have to say a little bit more, and we have to bring into the play the concept center of mass. So the center of mass. The best way to start on the center of mass is just to define it as the balance point. This is a really simple demonstration. I'm just balancing a ruler on my finger, but you know, the ruler has a weight. Throw it on the scale, find out how much it weighs, which I'm not literally interested in right now, but we know it has a certain weight, a couple newtons. And I'm balancing those couple newtons right at the center of this ruler. So we're just going to analyze that for a moment. Center of mass, first of all, the balance point. And I've got the ruler, and I'm balancing it here. I'm going to define that center of mass. It's a star, and I'm balancing it here on my finger. I'm balancing it on a wedge. Okay. And the thing is, what we want to ask is, what are the forces acting on the ruler? Okay. So forces on the meter stick, and now we have practice with this now, so we say, good. There's its weight, and there's a normal force. Right? And you'll notice the meter stick is not twisting or anything, it's just at rest. So you got the weight and the normal force. Very quickly, F net equals 0. So N minus mg equals 0. The normal force is just mg. Okay, we've been there before, but it's now balancing. And what we can say about the weight, right? This mg is just the weight. We can say the weight acts at the center of mass. This is a literal proof of the fact. Balance point. So the operational proof, so to speak. So the weight acts at the center of mass. Now there's a technical point where you could say it's the center of gravity. For our class, we're going to identify center of mass and center of gravity. Don't worry about that. Okay. So the weight acts at the center of mass. The weight, I say. And there's the proof. Now, suppose we have the same ruler. Okay, so we're going to take the same ruler. This is point 3 of our list right there. I'll go ahead and erase all this. So we're just continuing this example. We've got the same ruler, the meter. We now know that the weight is concentrated here. And suppose we want to balance it on this wedge. Okay. If I try that, of course, it just falls. Is that there? Yeah. If I try that here, it just falls. And you're saying, well, you're going to have to hang something from this side. You have to use some other force, so the weight m here, I'm going to have to take another mass. I'll just call it m1, and then apparently I can balance this. Point is that the weight is still acting right there, even though the wedge is acting right here. The weight is still acting at the center of mass. Okay. So note on or at the center of mass. Okay, so now I can give the actual formal definition of the center of mass. So practically speaking, it's a balance point. Formally, R, I'll just write Cm. It's a point, so it's a vector. It's equal to the sum of all of the masses times their distance from an origin divided by the sum of all of the masses. So here we think of an extended body that's composed of many masses. Just like with the ruler, you know, we could chop it up into many masses. So center of mass is this sum here divided by those. And what you'll see is it will give you the balance point every time. So I'm going to do an example for the center of mass. Like I said, it's the formal definition. Suppose we have along this x-axis, we have a mass at 1, a mass at 2, and a mass at 3 units, whatever they are. Okay. And if these masses are equal, and if these distances are equal, then everyone's going to say, yeah, the center of mass must be in the middle here. Because 3 masses on a wire, we could balance right there in the middle. Now, you don't necessarily see it from this expression, but let's just go ahead and calculate it. This time, our center of mass is just along the x-axis, and it's equal to m times 1 plus m times 2 plus m times 3. Because we're taking this as the origin, divided by m plus m, which is 3m. So what do we get? 3, 4, 5, 6 m divided by 3m equals 2. And 2 units of length, 2 meters or something, but I didn't want to write too many m's here, okay? So it's just 2 units of length. Right where we said it would be. And you could make more complicated examples, and it's always going to be the center of mass. If we had nothing here, in fact, this is a good example too. I'll do it in red. So let's get rid of this one. And I will use just this piece of board right here. If we had nothing where the 2 is, then we would have x center of mass would be equal to m times 1 plus m times 3 units of length. Right? I'm just using this formula here, divided by m plus m, which is 2m. And again, you'd see we get 3 plus 1 is 4m over 2m would be equal to 2 units of length. Okay. 2 units of length, and that's exactly where the center of mass would be if you had say a really thin wire with 2 masses on the ends, right? It would be right there in the middle. Okay, so you can use this formula to calculate centers of mass. That's the beginning of understanding mass distributions. I'm going to check the time again. Okay. So again, this is that formal definition, and these were just a couple of examples calculating with it. We'll put a couple of these in the homework so you just get to practice. So the next thing we're going to do, now that we have the center of mass, and we've already talked about moment of inertia, we have to talk about torque. So torque is a twisting force. Okay. So this bar, if I just let go of it, it'll fall there. I have to actually exert a twisting force on it, okay, in order to hold it up. So that's a torque. And the way to study and understand torque is to use hand tools. So first of all, I'm just going to give my twisting force as a, put it in scare quotes, colloquial definition. We've got the twisting force here. The example is if you have a wrench and you want to tighten a bolt. Okay. So I will draw hexagonal bolt here, and I'll put a wrench on it. Okay. Maybe use some colors. But we're trying to tighten this thing. And there's the axis of rotation. Okay, I could be tightening this thing, and if I turn it clockwise, it's going to go into the wall, and this wrench is going to help me turn it clockwise. Maybe we can make this thing look a little more graceful. Slightly. Okay. So that's a wrench. Okay, everybody should use some hand tools sometime to get a feel for these things. Now, how do I get a twisting force? If I want to tighten this thing, there's my force. And if you've ever used hand tools before, you'll realize that the longer the handle is, the more I can twist, the more torque I can exert. Whereas if I were to exert my force here and pull down on it, it would give less torque. Okay, so this is a practical matter, and I'm going to go ahead and call this distance from the axis to where the to where the force acts. Okay, this is the axis. I'll call it R, and we're going to use the Greek letter tau. That's kind of a sawed-off T with a little wave on top. That's tau. So that's torque equals force times lever arm. So we often, when we write them in order, we write the R first. But it's a force times a lever arm. Force times lever arm. And under this definition, these two have to be perpendicular, comma, where F and R are perpendicular. So this is the basic definition. If you understand this, you'll understand all of the torque applications. And you'll notice, if I make this R longer, the torque is going to be greater. If I make the force larger, the torque's also going to be greater. And in practical life experience, if you use too big of a wrench on a little bolt, sometimes you can strip the threads. And what you'll do is you'll actually choke up on it and work it from here so you don't accidentally use too much torque. Okay. So hand tools are the way to go to understand torque. And in terms of the directions, the clockwise drives the thing in, and the counterclockwise with a standard thread brings it out. So torque, force, and lever arm, F and R are perpendicular. And what we're going to realize is, when we start to do dynamics, it's going to take a torque, it's going to take a twisting force to get this thing spinning. So the torque we're going to need in dynamics, we also need it in statics. So we'll do statics first. Use torque for statics first. Okay, I'm going to send this up. Okay, consult the clock. Give one more example, and then we'll get some problems for these concepts. An example, I'll call this statics, is if you just have to hold some masses at the end of it, in your hand, and this L shape here of my arm. Okay, that's what I'm going to draw on the board. I've got some masses here, and we have to ask ourselves, where are the axes and what's holding what up? Okay, so let's draw this. Very simple example. So here's the arm. There's the forearm, there's the hand holding the masses. So now we have mg, and where's the axis? Okay. Well, it's going to be here at somewhere in my elbow, right there. So I've got a torque, and we're going to use different color to label this. I'm going to use a length L1, goes all the way to there. So I have the torque, and it is a clockwise torque because this arm here is trying to go clockwise. Clockwise torque is equal to L1 times mg. Well, how come is my arm not spinning? It's because if this is the axis, let's go ahead and call this the axis, then there is a muscle force that's pulling up that way. I'm just going to call this F. And what is the torque now? The torque is that force times this small little lever arm, okay? So the counterclockwise torque, counterclockwise, is equal to, and I have to give this a name, L2, that really short length, times the force there. And the equilibrium condition is that these two torques have to be the same. So this force has to pull up enough so that this downward force can't twist the arm. So if you were to just completely abstract this, you'd have the following situation. You'd have mg here, and you would just draw F right there, and then this would be your L2, and your L1 would be this entire distance. And then I'll write equilibrium we would have to have mg L1 is equal to F L2. So that because of these different lengths, this force is much, much larger than that weight. It could be realistically 10, 20 times as large, okay? Because that length is so much smaller. And you saw it, it's just a literally physical example off of your body. Good, so next time we'll do the formal equilibrium condition, but this is a good example to start with. And I'm just going to consult the book now for homework number, what is this, 24? 25. So now we're told, we are in chapter 8. So homework number 25, chapter 8. Let's see what we can do here. Problem 4 is a good one. Have to think a little bit, shouldn't be hard. Okay. Now, I'm not doing any specific angles on this yet. So, just to keep it simple. Well, I am going to have to put some angles in here. No getting around it. Okay, number 19. You have to extend the definition of torque. You're going to have to look that up in the book. I'll come back to that, of course. 19 is similar to what I just did, except the angles are not right angles. And you know, I'm going to do number 27. So we're doing equilibrium conditions, and I'll probably work these in the next lecture, as a matter of fact. But give them a try, and then I'll work them for you guys, just as part of our discussion. Okay, good. I'm going to write this down. 8, chapter 8, 4/1927. Okay, good. See you guys next time.